Good afternoon, my name is Evan Chambers, and today I'll be talking about Faraday's law and magnetic flux. First we'll look at magnetic flux, referred to as phi, the Greek symbol, and we know that it's equal to the vector B cross A, which is field times the cross-sectional area, otherwise known as BA cosine theta. Now this cosine theta refers to the angle at which the wire is relative to the field. So as we look at this right here would be the wire ring, and these is the field lines passing through. If we imagine that we are looking at a sideways view of this ring, then we can see that at this is an angle of 0 degrees relative to the field, so we have a cosine of 0, which is the same as 1, so we end up with a phi equal to the field times the cross-sectional area of the ring. And if you continue on, you see that it becomes parallel with the field as it goes across, which leaves you at a field times area times a cosine of 90, which is 0, so you end up with a phi of 0. This makes sense if you think about it conceptually, because as the ring moves closer and closer to parallel with the field lines, that gives you less amount of area for the field lines to pass through. This will give you a smaller phi. Taking that into account, we can now look at Faraday's law, which states that a voltage accumulated around a closed circuit is proportional to the magnetic flux it encloses. What this means is that the voltage, or the EMF, the electromagnetic force we are looking at, will be proportional but opposite to change in phi over the change in time, which comes out to be the same as the change in field times area, cross-sectional area per time. Now this negative right here, this refers to Lenz's law, which states that every force there has to be a reactive force or an opposed force. So as a field goes through the wire, we will also see, as a field passes through a wire, we'll also see a smaller but still existent opposed field be opposed. We'll also see within the wire an opposed current. Another thing that's important to take into account is the ratio between field and time when looking at EMF. You see, I wrote here, as time decreases, the EMF increases, which means that if the field is passing through, the less time it's passing through, the more EMF you're going to get. On the same principle, if it's a greater field being passed through, it doesn't matter if it's a greater time, you'll still end up with a greater EMF. Now EMF, or electromagnetic force, it's basically the same as voltage. If you look at here, I checked the units, which for all you underclassmen I recommend doing all the time. I go, EMF is the same as dBA over dt. When you take those units, you find field is in Teslas, and cross-sectional area is meters squared over time, which is seconds. You can take this equation and break it down a little bit further to Teslas is referred to newtons times seconds over meters per times coulomb. And then when you plug that back into this equation, or back into these units, you see that you can cross out seconds and meters squared in meters, and you end up Newton meters per coulomb. This is also referred to as joules per coulomb or volts. This is an easy way to double check the fact that EMF is in fact the same as voltage. So now that we know that we're looking for voltage, we can read a question. So, what is the induced EMF through a wire ring as magnetic field drops from 5 teslas to 0 teslas in 1 second? If the wire ring has 0.25 meter radius and is perpendicular to the field. So, here's the wire ring, here's the radius of 0.25, field passing through perpendicular to the ring. And we're going to calculate this by breaking down. We're going to go EMF equals negative d phi over dt, the BA over delta t. Because the cross-sectional area remains constant in this problem, we can just pull it out and look at the negative area times the change in field over the change in time. Because it's a circle, we know that the wire cross-sectional area can be found by pi r squared. Then when we plug in the numbers, I ended up with 0.98 Tesla meters squared per second. Make sure that we have volts. We can double check with the units again, and we find that we ended up with meters. We squared, which was squared, and then your teslas over seconds, which teslas meters squared per second, we know from this equation, this ratio that we went out to, does in fact equal volts.